Let's clear the board and do a couple more examples so that it's absolutely clear how to implicitly differentiate functions. Let's try an example that is on your lecture notes in section 5.8. That's y to the power of 5 equals sine x. But to make it a little bit more complicated, let's add a few terms. Let's try to implicitly differentiate this. Step number 1 is you write this and you give some space to apply the derivative operators. In this case, y plus y to the power of 5 equals sine of x minus x to the power of 4. You now apply the derivative operators to the complete left side and to the complete right side. In this case, it's sort of still splitting between y and x. In the next example, it becomes slightly more complicated, but not that much. It just means that you will need to move terms from one side to the other. Remember that for implicit differentiation, and in an exercise, a problem or a question in an exam, you'd be even told this directly. But in this case, we are assuming that y is a function of x, but we do not have access to this specific definition, which means that whenever we differentiate y, we need to use chain rule and we need to keep the dy dx because we don't know what f of x really is. Step number 2 is then determining these derivatives. Let's start with the left-hand side. In this case, the derivative is very easy. This is just 1 and then times dy dx. From now on, I will not write the 1, but I just want it to be absolutely clear why differentiating a y term leads to dy dx. Technically, it leads to 1 times dy dx. And in this case, this is a power rule, so this is plus. That's 5y to the power of 4, again times dy dx. So we've completed the left-hand side. And on the right-hand side, we have terms that only depend on x, which means we will not be using chain rule. And the derivative of sine x is cos x. In this case, we're just using the subtraction rule and also the power rule. This means we get minus 4x to the power of 3. Typically, the next steps that you need to take include grouping the dy dx terms and then sending everything to the other side so that you can find your answer. In this case, we see that if we take dy dx and group the terms, we have dy dx of 1 plus 5y to the power of 4 equals cos of x minus 4x to the power of 3. And we're almost there. In this case, this will be our final step, which is take this and dividing by the other side so that we can finally get dy dx. So this means that dy dx for this implicit function is given as cos of x minus 4x to the power of 3 divided by 1 plus 5y to the power of 4. And as I've pointed out in a previous video, most of your answers when a function cannot be explicitly defined will just look like this, and that is okay, which means you do not need to get your final answer in terms of just x, and I hope that is absolutely clear. By now, you should really be getting the hang of it, but let's try a final example that you can also find in your lecture notes. Let's try to differentiate this implicit function. By now, it should be obvious the reason why this is an implicit function. That is because we do not simply have y equals 2 and then a bunch of terms and x. If you know how to do it now, I don't even need to explain the detailed steps. So I'm going to skip some of them, and it's more than okay that when you implicitly differentiate, you don't need to say 1, 2, 3, but it is important to still show your intermediate steps, like I will try to show. First thing you should do is write the same expression, then apply the derivative operator to both sides, and then you calculate the derivatives, remembering that y is a function of x, and therefore you need to use chain rule. In this case, starting from the left, this gives you 2y dy dx. Then we have a term in x, which means you can differentiate it completely. There's no need to leave dy dx because x is already the variable. Get 3x squared minus, and similar way for this term, 3y squared. Do not forget the dy dx because y is a function of x. And this is a constant, it disappears, it is 0, I will not write it here, you're okay to do it, you don't have to. And on the other side we have 3y, which means we get 3 dy dx. The slight difference from the previous example is that in this case we have dy dx terms in both left and right. So we need to pull them together, and an easy way to do it is to take anything that does not contain dy dx to this side, and anything that contains dy dx, take it to the left hand side. Once you get to this stage, you're almost there. All you have to do is to take the dy dx out and then take the term that you're multiplying it by to divide by the other side, which I will now do. And in this case, I'm just showing you that as long as you show the intermediate steps, it would be okay to go for this, provided that you check your steps. In this case, you would be having dy dx times 2y minus 3y squared minus 3. So I'm just going to take that term already, and I am dividing by it. So that's 2y minus 3y squared minus 3, which gives you your final answer, which you can check on the lecture notes to see that it is correct. I would strongly recommend that you do attempt more of these examples, and as long as you focus on the fact that y is a function of x, and that you always use chain rule, which means whenever you differentiate a y, you differentiate it and then you multiply by dy dx, all the other steps should be relatively straightforward. But if you do have questions, just let me know.